Hi everyone, my name is Jessica, and today I'm going to be talking about tips and tricks, troubleshooting sample preparation for electron diffraction. And I wanted to start off by saying that this is a really big topic and not something that I could cover in any sort of comprehensive way in a few minutes. So the idea here is to highlight a few examples of challenging samples and what we were able to do to overcome those challenges to help you generate ideas for what's possible with electron diffraction. First, I want to talk about sort of standard sample preparation. And that general workflow would involve taking a powder crystalline material, placing that between two glass slides, and agitating that powder between those two glass slides to mill the particles down to a smaller size. We would take this powder and tap a TEM grid that we're holding with tweezers onto that powder to load it. And from there, we can put that onto a specimen holder, insert it into the diffractometer, and collect our data. And this type of approach works well for air-stable dry powders that we have available in milligram quantities, but there's a number of types of samples that may be amenable to analysis by electron diffraction, but may prove challenging in actually just preparing the TEM grid itself. And that can include samples that are sensitive to solvent loss, they're air or moisture sensitive, present only in submilligram quantities of material, or they might be suspensions within high boiling solvents or coated in oils. And many of these challenges can be addressed just by getting a little bit creative with the sample preparation process. The samples that people might be most familiar with electron diffraction are those that are sensitive to solvent loss. This sensitivity can range from samples that slowly degrade under vacuum at room temperature to those that can really not tolerate any loss of solvent before you start to lose crystallinity. For the less sensitive samples where you can handle them as dry powder, you can subject them to the standard type of sample preparation, where the only change here would be that you cool the sample prior to inserting it into the electron diffractometer with a so-called cryotransfer process. If you were to try and analyze these samples at room temperature, you might see weak or no diffraction, whereas if you just cool the sample before exposing it to the vacuum, you can now get high-resolution diffraction that'll help you solve a structure. And so this is something to keep in mind anytime you have a sample that perhaps by powder diffraction you saw great data, but when you're analyzing it by ED, you're not seeing samples that diffract strongly. And so this can be due to vacuum sensitivity. The more extreme cases require a bit more change to the sample preparation pipeline. And that's because you actually can't get them into this state. By the time you have a dry powder, the material may have decomposed. And so now you're left with two questions. One is, how do I make smaller grains, since we want these submicron sized particles, as well as how do I get the sample onto the specimen holder before it decomposes? In order to make smaller grains, we can make those within a suspension of solvent. And that can include things like vortexing a suspension, vigorous pipetting, where you can take a narrow tip pipette and pipette the solution back and forth to agitate it and physically break up the particles, sonication of the samples, or as I have photos of here, a manual grinding of the suspension. So here we have a vial that contains our suspension of particles along with a disposable glass pipette. We can put that pipette into the vial and agitate the particles against the side of the vial in a very similar way to the sort of two glass slide technique, which allows you to physically grind those particles into a smaller size. And another strategy for this would be using crystallization droplets, where you can take something like a micro tool to break up larger crystals into these smaller sizes. Once you have crystallites of sufficient size, from there you have a couple of options on how to actually apply them to the TEM grid. And for that, we'll borrow this technique from originally cryo-EM, but more recently has been used to study protein microcrystals by electron diffraction. And with that, we take a TEM grid and we use this glow discharge technique to make the grids more hydrophilic. From there, we can pipette our suspension of crystals onto the grid, typically somewhere around 1 to 3 microliters of a suspension. And from there, we blot the sample. And this blotting can be done manually by actually just holding filter paper and touching the grid, or there are instruments that do this that are available at most cryo-EM facilities. And this blotting time can range anywhere from 1 to 20 seconds. And typically, the longer you blot the sample, the less solvent there's going to be on the grid in the end. And from there, we're going to plunge freeze the sample. And there's a couple of options here, one of them being plunge freezing in liquid nitrogen. And liquid nitrogen is great for plunge freezing if most of your solvent is blotted away. You can go directly into liquid nitrogen. If you're trying to leave a thin layer of solvent onto your grid because your crystals are especially sensitive to solvent loss, then you might need to turn towards something like liquid ethane. And the reason for that is because liquid ethane cools about 50 times faster than liquid nitrogen. So if you have a thick layer of water, for example, you can actually freeze your crystals within the water before the water itself crystallizes, which means that you can collect diffraction data on your sample while it's still within water. And even though this technique has largely been explored and used for protein crystals that are in solutions of water, people have also begun to look at the vitrification of organic solvents. And so I have a reference here that shows the vitrification of organic solvents in either liquid nitrogen or liquid ethane. And so this could be useful, for example, if you're looking at moths and you don't want your moth to dry out before you analyze it. A different type of challenging sample would be those that are air or moisture sensitive. And here I've highlighted a structure from Christian with the University of Denmark, where they solved this palladium-0 structure that was air sensitive, and they were able to locate these small microcrystals and solve the structure from those. The sample preparation included putting some powder inside of a glove box into a vial, sealing the vial, and then shipping that sample off. Once the sample was received, then the vial was opened, and the standard sample prep took place with an emphasis on go fast so that you can try and outrun oxidation and find some crystals that haven't decomposed, even if some already have. And while this approach can work, another technique that we've started to use recently has been actually having people prepare their grids inside of the glove box. So you can take TEM grids and grid boxes and ship those, and these can be brought inside of the glove box to actually prepare the TEM grids under an inert atmosphere. Once those TEM grids have been loaded and a lid has been placed onto this grid box seen here, you can seal that within a 20 milliliter scintillation vial, which is commonly available in most glove boxes. And from there, the samples won't be opened until they're either already in liquid nitrogen or about to be poured into liquid nitrogen. So the amount of exposure to air is significantly reduced compared to standard sample preparation techniques. If you don't have a glove box, there are other strategies for mitigating exposure to air, and that includes something like an argon-filled container. Argon is great for doing air-free work because it's denser than air, so it displaces oxygen. And you can actually place your grid, tweezers, and sample all within a container that's filled with argon to minimize the exposure to oxygen and water vapor while you prepare the sample. An alternative to that would be a stream of inert gas. So you can have your grid and your tweezers underneath a workstation where, for example, a funnel is hooked up to a stream of gas, and you can gently blow a stream of this gas to sort of blanket the sample in argon or nitrogen to, again, try and displace oxygen and water vapor and extend the lifetime of your sample as you're trying to get it onto the sample holder. Next, we'll be talking about small quantities of analytes. And this topic in particular is near and dear to my heart because I've done a lot of work in the past with natural product samples. And a key feature of natural product samples is that they may only be available in sub-milligram quantities of material. And so you may have no other techniques available to you other than mass spec, maybe NMR, to actually determine what your structure is. And so actually working with this small amount of material, even though the amount of sample that we analyze when we're collecting data on a crystal with electron diffraction is incredibly small, it tends to be the actual preparation of the grid that is most challenging with this small amount of material. And so to handle them, samples are typically handled as suspensions or solutions at this scale. A couple of different ways to look at samples on this small of a scale would be actually taking a step back and thinking about the crystallization experiment itself. And the reason for that is you may not, after you do a crystallization trial, have enough material to really determine whether that crystallization trial was successful or not. So a technique that we've employed before is this so-called single container crystallization. It's fairly straightforward in that you take the majority of your material into one container. You will test some sort of solvent condition, either by slow evaporation or vapor diffusion. And from there, you'll take an aliquot of that material, and in order to determine whether your crystallization was successful or not, you actually use 3D-ED as your screening tool. So you can take a small portion of that crystallization trial, put it onto a TEM grid, collect data on a few different particles, and determine whether you're able to get high-quality diffraction or not. If you're not able to get high-quality diffraction, then you go back to the original sample where you could remove all of the solvent and try a new condition. Or, in some cases, you'll find that your crystallization did work and you're able to solve the structure directly from this grid. And so this is useful if the amount of sample that you have is incredibly limited. An alternative strategy would be to do an on-grid crystallization. And in this case, you can simply pipette a solution of your sample onto the TEM grid and allow it to slowly evaporate. Or this study here from the Gonin lab at UCLA, they were able to perform these hanging drop experiments directly onto TEM grids with these specialized holders. And so in this case, you would then take that grid and then prepare it according to sort of standard protein microcrystal sample prep methods. And even though those single crystallization trials might seem really tedious, I just wanted to emphasize why we would do something like this. And to do that, I wanted to point out the 3D-ED structure of lamivudicin C, which was solved in 2021 as a collaboration between the Herzon group and the Nelson group. And lamivudicin C and the entire family of lamivudicins have been studied for about 20 years, and no crystal structure was ever successfully solved. And as you can see, these are quite complex molecules, and their connectivity was assigned by NMR. And despite years of study and trying to synthesize these compounds, no one was ever able to successfully synthesize it. And it wasn't until the 3D-ED structure that they realized there was a misassignment in the original NMR structure. And this structure was solved using nanograms of material with microD. And so even though it is a lengthy process, it can solve some really challenging structures that there may be no other way to solve a crystal structure of. Additionally, we can work with samples that might look something like this, where I like to say you don't have to be happy about it, but you can analyze it. So this is a mixture of crystalline material with some sort of oily contaminant. And these viscous non-volatile solvents or impurities can be a challenge because if you try to take your TEM grid and simply tap it to this material, a lot of times you'll just wind up leaving behind the polymer film on the grid and you can't actually get it on there, or if you do, it's all clumped up together. And so here, the tools that you have available to you would be anti-solvents and blotting. And so this is really a small-scale purification by filtration, and I'll explain what that means a little bit more in depth. So how this would work is that you would identify a solvent. I like things that are a little bit more volatile, so hexanes is a great solvent oftentimes that doesn't dissolve your crystallites, but is ideally miscible with something that you want to remove. So if you're trying to remove DMSO, then water could be a good option. If you're trying to remove these non-polar oils, then something like hexanes could be useful. Once you've identified your solvent, then you can deposit that solvent onto a sticky mixture like the one shown on the right, and agitate it with pipetting to try and pick up some of those particles and dissolve some of the oils. From there, and I'll show a video of this next, you'll place it onto a TEM grid and wick away the solvent. And so this is a video showing how that process works, where you would take your suspension of particles and deposit it onto a grid. And from there, before it completely evaporates, you want to use a piece of filter paper and touch it to the solution, actually wicking away the solution itself. And you might be thinking that I just removed everything that I just put onto the grid, and that's why I have a second perspective of the same process, where in this case I'm again depositing that solution, and you can see some of these microcrystals floating in that solution. And when I take my filter paper and blot the sample, then a lot of these crystallites are still left behind. And once you've done that process, you can repeat it as needed. You could even, after letting the grid dry, you could take a look at it under the diffractometer, and if you still see too many impurities, you could take it back and repeat. But in the end, you want to allow the grid to evaporate to dryness, or if it's something that is not only a mixture with oil, but it's also something that you don't want to completely dry out, then you could freeze with the solvent as well. And the last thing that I wanted to point out with this is that you can see a low mag image of my grid here on the left, and there's a lot of droplets of some sort of oily impurity, and if you go to those regions, you may actually find suitable crystals within those regions, and you can collect data from those as well. And so to just kind of offer a summary of what we've talked about today, we're covering things from standard sample preparation to strategies to addressing other types of challenges, including things like solvent loss, air, moisture-sensitive samples, what to do when you only have a small amount of sample, or samples that may be coated in some sort of oil or high boiling solvent. And so these are just some of the strategies that can be used to address those. And of course, there's so many other things to talk about from the grids themselves onwards. And so if you have any more questions about sample preparation that I can't answer in the next few minutes, definitely feel free to reach out and I'd be happy to answer those over email as well. Thank you so much for your time.